Good day, everyone. So we're reviewing Wetzel's Limnology textbook. This is edition number 4, and today we are starting on chapter 14, the nitrogen cycle, with Michelle A. Burford with the Australian Rivers Institute in Nathan, Australia, and with Jing Lu with the School of Environmental and Sciences, Griffith University in Nathan as well, Australia. So let's get started with the introduction. Nitrogen, or N, is abundant on the surface of the Earth, but less than 2% is available to organisms. A major source of nitrogen input to streams and lakes is from surface land drainage and groundwater sources. Atmospheric sources and nitrogen fixation are other mechanisms that contribute nitrogen. An obvious loss from freshwater systems is via inorganic and organic, both dissolved and particulate, compounds in effluents flowing out of catchments, watersheds. Further losses occur as a result of the permanent burial of partially decomposed biota and inorganic and organic nitrogen compounds adsorbed to particulate matter in the sediments. Nitrogen can also be lost by the volatilization of compounds from the water surface, for example, ammonia, NH3 at high pH, and as gaseous nitrogen forms mediated by microbial processes. Nitrogen undergoes many complex reactions in aquatic systems, and our knowledge of the importance of a wide range of physical, chemical, and biological drivers of these reactions continue to grow over time. The following sections of this chapter focus on sources, transformations, and sinks/outputs of nitrogen from a range of freshwater systems. Before we move on to the next paragraph, let's look at these tables and figures. So figure 14-1. Simplified nitrogen cycle showing the complexity of nitrogen transformation in freshwater. Nitrate, NO3 minus, is nitrate. NO2 minus is nitrite. NH4 plus is ammonium. NH3 is ammonia. N2 is dinitrogen. And DNRA is a dissimilatory nitrate reduction to ammonium. Anamox is anaerobic ammonium oxidation. So what we have here, let's start with, so we call that dinitrogen, okay, N2 here. So N2, there is nitrogen fixation that results in organic ammonia right here, and organic ammonia can go through ammonification to ammonium, or ammonium can go into assimilation, which forms organic ammonia. Ammonium can result in anamox, which is anaerobic ammonium oxidation. So this is an anaerobic process without oxygen. Or ammonium can undergo aerobic nitrification, which results in nitrate. Or nitrate can go into DNRA, which results in ammonium. So DNRA, once again, is dissimilatory nitrate reduction to ammonium. So we have nitrate reduction here to ammonium, and dissimilatory. And then here, it looks like there's a step which includes NO2, which is nitrite, and nitrite can undergo this process resulting into anamox. And then nitrate can undergo anaerobic denitrification into dinitrogen, or there's a middle step, nitrite, through anaerobic denitrification that was formerly nitrate, then can result also in dinitrogen through this, I think, anamox process, although the presence of those dashed arrows compared to the undashed arrows is a little unclear. Table 14-1. Definition of major nitrogen transformations and its chapter section. So we won't go into the chapter section, you can review that yourself. So we have nitrogen transformation, nitrogen fixation, atmospheric process definition. So atmospheric nitrogen is converted by bacteria or cyanobacteria to ammonia. Ammonification, same as mineralization. So bacteria convert organic nitrogen to ammonium. Assimilation, organisms assimilate ammonium and convert it to organic nitrogen. Aerobic nitrification, biological oxidation of ammonium to nitrite, followed by the oxidation of nitrite to nitrate. Anaerobic denitrification, microbes reduce nitrate ultimately to dinitrogen and through a series of intermediate gaseous nitrogen oxide products. Disseminatory nitrate reduction to ammonium, DNRA same as nitrate to nitrite, ammonification. Microbes oxidize organic matter and reduce nitrate to nitrite, then ammonium in anaerobic conditions. Anaerobic ammonium oxidation, or anamox, microbes convert 1-to-1 molecular ratio of ammonium and nitrite to dinitrogen in the absence of oxygen and without carbon supply. Table 14-2, nitrogen species and their chemical formula. So we have volatilized ammonia, NH3, ammonium, NH4+, hydroxylamine, NH2OH. So this is NH2 with a hydroxide. Nitrite, NO2-, nitrate, NO3-. So we have one additional oxygen in case of nitrate. Dissolved organic nitrogen, or DON, not available. There's not a formula for it. Particulate organic nitrogen, PON. Particulate inorganic nitrogen, PIN. Dinitrogen, N2. And nitrous oxide, N2O. And what do they have? These forms of nitrogen are a group of compounds rather than individual chemicals. Yeah, so those here. I believe that's what they're referring to. So combined nitrogen occurs as ammonium, NH4+, hydroxylamine, NH2OH, nitrite, NO2-, nitrate, NO3-. Ammonium can range from undetectable levels to 5 milligrams per liter. In surface waters, with concentration in unpolluted waters typically on the low end of this scale. Concentration of nitrate range from the undetectable levels in unpolluted waters to 10 milligrams per liter or above in polluted waters. Groundwater may be an important source. Nitrite levels of natural oxygenated waters are generally very low, in the range of 0 to 0.01 milligrams per liter. Concentrations of nitrite increase in the anaerobic hypolimnion of lakes under reducing conditions, and in streams and lakes receiving heavy organic matter pollution. Dissolved organic nitrogen, DON, much of which occurs in forms resistant to rapid bacterial degradation, commonly accounts for more than 1/2 of the total dissolved nitrogen, or TDN. Much of the particulate organic nitrogen, PON, is bound up in algae, bacteria, and detritus, and the relative contribution to the total nitrogen, TN, load of a waterway can vary substantially. Particulate inorganic nitrogen, where nitrogen is absorbed to colloidal and particulate matter, can also vary substantially in its contribution to the nitrogen load between water bodies. Lake productivity is linked to nitrogen concentration, and this productivity can be categorized to provide useful definition of scales of productivity with inferences about ecosystem health. Ammonium, or NH4+. Much of the NH4+ in aquatic systems arise as the primary end product of the decomposition of organic matter by heterotrophic bacteria from the deamination of proteins, amino acids, urea, and other nitrogenous organic compounds. Intermediate nitrogen compounds are formed in the progressive degradation of organic material but rarely accumulate because deamination by bacteria proceeds rapidly. Phagotrophic protists, particularly bacterivorous flagellates, can appreciably accelerate the regeneration of ammonium by the consumption of bacteria and the release of ammonium ions. Ammonium can also be generated by dissimilatory nitrate reduction to ammonium, as well as will be discussed later in this chapter. Although ammonium is an excretory product of higher aquatic animals, this nitrogen source is quantitatively minor in comparison to that generated by bacterial decomposition. In addition to ammonium, undissociated ammonium hydroxide can also be present, which is highly toxic to many organisms, especially fish. However, the proportion of ammonium hydroxide is typically low at intermediate pH and temperatures. The approximate ratios of ammonium to ammonium hydroxide are as follows: pH 6, 3000 to 1, pH 7, 300 to 1, pH 8, 30 to 1, and pH 9.5, 1 to 1. So we can see that, as the pH is increasing by a factor of 10 every time, the ratio is decreasing by a factor of 10 as well. And so therefore, we have the same amount of ammonium to ammonium hydroxide at a pH of about 9.5, which is rather rare in natural waters. So let's look at table 14-3. General relationship of lake productivity to mean concentration of epilimnetic nitrogen. ND is no data. General level of lake productivity, change in alkalinity in epilimnion in summer in milliequivalents per liter, inorganic nitrogen in milligrams per meter cube, and approximate mean organic nitrogen in milligrams per meter cube. Ultra oligotrophic, so that means very nutrient poor, and so therefore there will be very low amount of nitrogen. The change in alkalinity is less than 0.2. The inorganic nitrogen in milligrams per meter cube is less than 200, as well as the mean organic nitrogen. Oligomesotrophic, 0.6 in the change in alkalinity in the epilimnion in the summer. Inorganic nitrogen is between 200 and 400, and the same for approximate mean organic nitrogen. Mesoeutrophic, 0.6 to 1.0 in the change in alkalinity in the epilimnion in the summer. The inorganic nitrogen is between 300 and 650 milligrams per meter cube, and the approximate mean of organic nitrogen is between 400 and 700. Eutrophic, no data for the change in alkalinity. Inorganic nitrogen is between 500 and 1500, and the approximate mean organic nitrogen in milligrams per meter cube is between 700 and 1200. Hypereutrophic, so that means very nutrient rich, greater than 1 in the change in alkalinity. Inorganic nitrogen in milligrams per meter cube is greater than 1500, and the approximate mean of organic nitrogen is in milligrams per meter cube is greater than 1200. Detailed dissociation relationships with pH and temperature are given by Trussell and Emerson et al. Ammonium can be strongly sorbed to particulate and colloidal matter, especially in alkaline lakes containing high concentration of humic dissolved organic matter. At high pH, ammonia gas can be formed by the deprotonization of ammonium. The rate of ammonia volatilization from wetland has been shown to increase with increasing concentration of ammonium and pH of the water overlying the sediments, as well as with greater wind velocities and temperatures. The distribution of ammonium in freshwaters is highly variable regionally, seasonally, and especially within streams and lakes, and depends upon the level of productivity and the extent of pollution from organic matter. Although generalizations are difficult to make, concentrations of ammonium in well-oxygenated waters are usually low. In the trophogenic or photic zone, ammonium is rapidly assimilated by algae and represents the most significant source of nitrogen for the plankton in many lakes. The energy necessary to assimilate nitrogen by plants is lowest for ammonium and increases for other nitrogen sources such as nitrate and N2N for other nitrogen sources such as nitrate and N2N for nitrogen fixing cyanobacteria. Some experiments show that cyanobacteria can grow faster on ammonium, while others have comparable growth rates using ammonium and nitrate, as well as urea. Other studies show that nitrate uptake can be suppressed by ammonium concentration as low as 2 micrograms and NH4N, ammonium nitrogen, per liter. So as low as 2 micrograms per ammonium nitrogen per liter. A few algae, such as a species of Chrysochromiluna, a haptophyte, are apparently only able to utilize ammonium as an inorganic nitrogen source. So a haptophyte is a clade of algae, and an example is coccolithotroph. Turnover rates of ammonium can be in the order of a few hours. Thus, concentration of ammonium are commonly low in unproductive oligotrophic waters, in the trophogenic zones of most lakes, and in most lakes after periods of circulation. So let's review figure 14-2, generalized vertical distribution of ammonium and nitrate in stratified lakes of very low productivity, oligotrophic, and high productivity, eutrophic. Theta is temperature. So we have two graphs. We have a graph for an oligotrophic lake, and then we have a graph for a eutrophic lake. So this is a nutrient poor lake. This is a nutrient rich lake. In the y-axis, we have the depth, and on the x-axis, we have the values in magnitude. So the nitrogen, temperature, or oxygen. No specific units per se, but just the magnitude. So it increases going from left to right. So for the oligotrophic lake, the ammonium concentration remains constant and low. The nitrate concentration increase, and it increases probably in the metalimnion or possibly in the oxycline, because this is where the oxygen changes. The temperature decreases, and so once again it decreases in the area of the metalimnion, which may be concurrent with the area of the oxycline, and then the oxygen concentration increases slightly. Eutrophic lakes is a very different picture. The ammonium concentration increases with depth, and once again it increases with depth in the oxycline, where in the area where the oxygen concentration changes. The nitrate concentration decreases with depth and actually becomes zero at depth, and so that is the opposite from the oligotrophic lake, where we had an increase in concentration. Here we have a decrease in concentration to a value of 0. The temperature decreases with depth, which is about the same than oligotrophic lake, although you can see that it doesn't decrease as much than in oligotrophic lake. And then the oxygen concentration has a very different behavior than in an oligotrophic lake. In an eutrophic lake, we have a decrease in concentration of oxygen to 0 in the oxycline. So this is about it for today in our introductory review of chapter 14 on the nitrogen cycle. I will see you tomorrow. Thank you.